obtain general solutions to the heat equation on unbounded spatial domains. And so in the process, we had derived the heat equation fundamental solution, okay? And what this is, it's essentially the solution to, and I didn't tell you this the other day, but it essentially solves the following PDE with initial condition. So our nice heat equation, but then in the limit, as time goes to 0, you recover a delta distribution, right? So here's your x, and here's your u of x0. And we just have a function that's 0 everywhere except at x equals 0, where it's undefined. But if you integrate this distribution, you get back 1, okay? And this is going to be helpful for constructing general solutions when we have an initial condition other than just a delta distribution, okay? So the IVP that we wrote down on Monday, we still have not shown how to solve that. So our general solution here, right, which is the fundamental solution, has that u is equal to this function phi of xt, and this is equal to 1 over the square root of 4 pi k t e to the minus x squared over 4 k t, okay? And it goes from this, very spiky initial condition, as spiky as it can get, to something that smooths out over time until it gets just completely flat. So, let's say this is at, t equals t1, t equals t2, t equals t3, and this is x, and this is our, we're plotting u here. And as we progress forward in time, our solution is going to flatten out. It's going to become smoother. And in fact, as soon as we step away from the initial condition, what we should find is that we have, we basically have an infinitely smooth solution, okay? So fine, okay? We also talked about some properties of this solution, but now how do we use it to piece together solutions to the initial value problem, okay? So to solve what I'll just call the Cauchy problem, okay? This is just our well-posed initial value problem here, okay? We're gonna focus on 1D, as I do above, and our initial condition g of x. I'm actually not gonna put any constraints on it, because actually even if it's non-smooth, we surprisingly will get a smooth solution, okay? So how do we solve this? So the principles are as follows.
Professor?
Okay. Yes.
Should we establish a continuity condition between u of x comma 0 and u? Like the two solutions should give the same result at x comma 0. I mean, phi of x comma 0 should be u basically delta x, right?
Absolutely, yeah. So yeah, I think what you're saying, AJ, is that the limit as t goes to 0 from above of u of xt is equal to u of x0. Is that what you're saying?
Yes.
Yeah. Yes. So we will show that this happens when we construct our solution using the fundamental solution. Yeah.
Sure.
Okay. So I'll get to that just after I talk about how to construct the general solution from the fundamental solution. But yeah, thanks for pointing that out. So so by translation invariance, right? of our original PDE, right? Phi of x minus y t also solves just the PDE, right? I'm not saying that it solves the initial value problem, but because my operator is translation symmetric, right? I'm on an unbounded domain. I should be able to move the solution around anywhere and it should still be a solution. This is the principle that we use to get our fundamental solution to the wave equation in Rn, okay? Also, so is g of y, phi of x minus y t, okay? Because, right, g of y does not depend on x, right? So I can shift around and I can also scale up and down my function by g of y, and it should still be a solution. A homogeneous linear equation, you can always rescale it and that will still be a solution to a homogeneous linear equation, okay? So putting these things together, okay, by linearity, okay, and homogeneity, and also, so is the following solution. U of xt is equal to just the integral, okay, over phi integrated against g, okay? Because all this does is it shifts it around, it scales it, and then it adds up all of these solutions, right? I mean, an integral is just sort of infinitely adding up solutions, right? So this should also solve the PDE, okay? Now the trick is that this also satisfies our initial condition. Why? Because of the properties of phi as t goes to 0. It behaves like the delta function. So if we integrate it against g of y, then if we integrate delta of x minus y, we should get back g of x, okay? So what have we done? We've said, well, I know what the fundamental solution is. I know that I have these linearity, homogeneity, translation invariance properties. I can superpose a bunch of solutions that then I know generate an initial condition, well, a function that limits to my initial condition, as AJ was remarking on before, okay? So essentially, we've summing, or, you know, essentially that's what integrating is doing, okay, across many solutions, okay? So this is kind of a back of the envelope proof, okay? And we get that u of xt is equal to phi of xt convolved with g of x, okay? So this is our convolution, okay? Convolution is just taking a function, shifting it by some amount, and then, you know, integrating against that shift against another function, okay? I'm going to advance the slide, okay, just to make one more remark about this solution. And that's that, note, okay, the convolution with phi of x t goes to delta of x at t goes to 0 from above, okay, allows, okay, u of x t, I want to write that as a limit, goes to g of x as t goes to 0 from above, okay? Basically because the integral from minus infinity to infinity of delta of x minus y, g of y dy is equal to g of x, okay? This is just the definition of the delta distribution, okay? All right. So that's good, okay? We want to firm this up a little bit more and just look a little bit more closely at how this all fits together. So let's frame that in the context of a theorem next. Okay, before I go on, is this sort of back of the envelope sketch clear? Or are there questions about this?
Are we gonna justify more rigorously that the integral is still a solution? Because I know we have this, of course, for like a finite linear combination, but I'm not really. I'm wondering what kind of tools we need, or if there are any hidden criteria on G or phi that we should know.
Yeah, so it comes from phi being continuous and uniformly bounded for t greater than 0. And so we can plug the solution basically into the PDE and basically apply what we already know about our fundamental solution and show that this convolution for the general solution also satisfies that. So first we want to show infinite smoothness. That'll be the first step in this next theorem. Then we're going to show that the thing that we've constructed does still satisfy the PDE, and then we'll show this limiting condition also, which requires a little bit more work. Yeah. Okay. So let's just jump into this theorem then. So then if C, let's just start off with somewhat of a restriction on G. Okay, just so we're not going too off base here. So we'll assume it's continuous. Okay. Then I want to call it star. I'll say then the general solution has these properties, okay? So first of all, item 1 is that U is continuously infinitely differentiable in X and in T. Okay, so this is my X and this is my T here, right? Second of all, U is going to satisfy my initial condition. Third of all, okay, the limit as xt goes to some x0, 0, okay, where x is in R and t starts off greater than 0. That limit is g of x0, okay, for x0 living in R, okay? So remember, what are we working with here? We have u of x t equals this integral, right? Phi of x minus y t, g of y dy, fine, okay? So these are the three properties that we have and can prove, okay? Let's start with the first one, okay? So the first one says that, let's say for n and m, they're integers greater than or equal to 0. The derivative, n times with respect to t, and m times with respect to x of u is going to be equal to what? Okay. Well, I can pass that through the integral, assuming that g is continuous, okay? And then for t greater than 0, that phi is going to be continuous and bounded, okay? Phi is just going to be a Gaussian, divided by t. Those are both positive continuous functions. G is assumed to be a continuous function, okay? So I can pass this derivative in here, and start taking, and bounded as well, and start taking derivatives with respect to phi, okay? So this always converges basically because the integrand is what? Well, it's a function that we know that's bounded and continuous, right? This Gaussian, right? This is a positive number for t greater than 0. This thing is a positive number, so it's just e to some negative number, okay? Bounded and continuous, times some polynomial. Remember that phi is just, 1 over some constant times the square root of t. As long as t is greater than 0, we don't have any discontinuities, we don't have any unboundedness, okay? And third, we've also assumed that g of y is continuous and bounded, okay? So this whole product then is continuous and uniformly bounded, okay? You could just bound this whole product by the product of their upper bounds or something like that, for instance, okay? On are going from some small number, call it alpha, up to delta, basically for some alpha greater than 0. Sorry, this would be a closed interval here, right? So anyway, that's the same thing as saying the open interval there, okay? So that means that I can take as many derivatives as I want, okay? Because this integrand essentially is always going to be bounded, okay? The second property is that
Professor, what does boundedness have to do with differentiability?
Because the derivative is defined by the integral over a function. So I need that function to be bounded in order for it to have a defined integral, essentially. If I have an unbounded function and I try and integrate over it, there's a chance I may not be able to define that integral. Yeah. Okay. So second property is that the derivative with respect to t of u is going to be given by the derivative with respect to t of phi convolved with g. But I know, because this is the fundamental solution, I've already showed that this should be equal to k times the second spatial derivative of phi. So I can write this as k times the integral from minus infinity to infinity of phi xx x minus yt gy dy, okay? And so if I work out then what uxx is, right? Uxx is just going to be given by this, right? I just take two x derivatives of my integral, and I can exchange the order of differentiation and integration, because again, phi sub t g and phi sub x x x minus y t, okay, are uniformly continuous. Okay, so I can exchange the order of differentiation and integration in that case. Okay, so to check property 2, all I had to do was just plug in my result, and show that it satisfies the PD. Okay, so now the part that requires a little bit more work is just going to be